Hello everyone, in this video we will be talking about unit 5. I will try to complete the unit in one video. I will not explain each and every detailed derivation which is given in the textbook because they are not all necessary. I will explain the important part and the important points to study only. Okay, I will not be talking about each and every terms in the textbook because some of the derivations are very lengthy. It will require 4 or 5 pages to derive, so it is not necessary to study everything in detail from this chapter. So the ones which I will be discussing in this video will be the important ones even for your exam. Now firstly, let me talk about center of mass. Center of mass. So what is center of mass? Center of mass is the point in the system where the whole mass of the system is supposed to be concentrated. Okay, this is called the center of mass. The point in the system where the whole mass of the system is supposed to be concentrated is the center of mass. If you go to church, what is the center of mass? For example, okay, the center of attraction, the center of mass inside the church is the pulpit, right? So just like that, the point in the system where the whole mass is supposed to be concentrated, that point is called the center of mass of the system. Now consider an object having two objects having masses m1 and m2, and so let the center of mass will be this point, right? The center of, let the object A have mass m1 and let the object B have mass m2, and the center of mass will be this one. So we will take the origin O. Okay, so the distance of the object A from this O, let it be x1, and the distance of B from the origin is x2, and the distance of the center of mass is x. Okay, so let this center of mass be C. So from the definition, how will we calculate the center of mass? Okay, the center of mass can be calculated by the formula. Let the center of mass be x. Okay, the center of mass can be calculated by m1 x1 plus m2 x2 by m1 plus m2. Okay, mass into distance x1 plus mass 2 into distance x2 by m1 plus m2. Okay, we don't have to study the derivation. This is how we can calculate for the center of mass of a system of two particles in a straight line. Okay, and when the particles are having equal masses, okay, when the particles are having equal masses, and in that case the center of mass can be easily calculated by x1 plus x2 by 2. Okay, so we can use this formula if the masses are equal. Okay, so these are the few important points that we can study about the center of mass. Now for the second topic, let us talk about for our second topic, let us talk about the conservation of linear momentum conservation of linear momentum and velocity of the center of mass of a system. Okay, conservation of linear momentum and velocity of the center of mass of a system. Now consider a system of n particles. Okay, consider a system of n particles. So there can be infinite number of particles, particles, and each of them having masses m1, m2, m3. Okay, dot up to mn. Okay, so if there are n number of particles in a system, and if the masses are this much, m1, m2, m3, dot mn, moving with velocities v1, v2, v3, dot vn. Okay, so their respective velocities is this one. Now suppose that the external force acts on the system. Okay, so in that system, if there is a force acting on it, so let that force be F. Okay, so since it is going to be external force. So let us write EFEXT. Okay, so to denote the external force. Now, so what will be the total linear momentum of the system? I hope you remember linear momentum. Linear momentum, we studied in previous units, it is P, right? So it is mass into velocity, right? So the total linear momentum of these n particles will be equal to m1 v1 plus m2 v2 plus m3 v3 plus plus mn vn, right? So now, according to Newton's second law of motion, what was the statement of Newton's second law of motion? The statement was that the external force if is the rate of change of momentum, right? That was the Newton's second law of motion. Now, from Newton's second law of motion, what do we have? Force is equal to rate of change of momentum, right? dp by dt. If you look back this unit, you will remember it. So now, if I am going to use this value of p vector, okay, from this equation, if I substitute this line over here, so it will be d by dt of, so what is momentum? It is all of this one, right? So it is m1 v1 plus m2 v2 plus up to mn vn. Now, in case no external force acts on the system, okay, in case no external force acts on the system, so what will that mean? It means that all of this value will also be equal to 0, right? If no external force acts on the system. So what does that mean? The differentiation of mass, the momentum, the linear momentums, the differentiation of linear momentum with respect to time is 0. So what does that mean? It means if after differentiating it, if we get 0, it means that this value is a constant value, okay? So we cannot differentiate a constant value, it will be 0. So if this differentiation of this with respect to time, if it is 0, that means that this value is constant, right? So it means that m1 v1 plus m2 v2 plus up to mn vn, up to n number of particles, it will be a constant, right? It will be constant. So it will be a constant vector. So for a number of n particles. So what does it means that from this we can know that if no external force acts on the system, then the total linear momentum of the system, if no external force acts on the system, then the total linear momentum of the system will be a constant, okay, will remain constant. Now, again, if m, capital letter M, sorry, m is not a vector quantity, if m is the total mass of the system, okay, so the total mass of the system, m1, m2, m3, right, the total mass of the system, if it is represented by capital letter M, and the total velocities of the system, again, if it is represented by capital letter V. So again, instead of writing momentum, we can simply represent it with the total value m into v. Mass into velocity is also momentum, is equal to m1 v1 plus m2 v2 plus up to mn vn. So again, this is a what? So since this is a constant value for if no external force acts on the system, so what does that mean? mv is equal to the total mass and the total velocity, means that the total linear momentum is constant, right? If no external force acts on the system. So that will give our statement, okay, for linear momentum. Conservation of linear momentum states that if in an isolated system, means that if there is no external force acting on the system, then the momentum of the system will be constant, okay? So that is the conservation of linear momentum and velocity of the center of mass of the system, okay? So it will also mean that velocity is constant, okay? Why? Because mass can change, right? The masses can change. If m into v is constant, since mass can change, it means that v is the one which is constant, right? So the momentum of the system, the conservation of linear momentum states that if no external force acts on the system, if the external force is 0, then the momentum is constant. and the velocity of the center of mass is also constant. Okay, so that will be enough for this topic. Now let us go to our next topic, which is moment of force or torque. Okay, moment of force or torque. Moment of force or TORQUE. Okay, torque. So what is this moment of force or torque? The turning effect of force about the axis of rotation. Okay, the turning effect of force about the axis of rotation is called moment of force. So here is a two axis, right? X-axis and Y-axis, two dimension. So if we are giving a force in the corner, okay, from a point O, if we take any point point P, then if we rotate this about the axis, right? Kil khat hey karum bang kilanita hey emergency light hi object ka omna like and force kan apply na tur kha ni ta se chon x axis le ki ma lampang y axis or y axis le ki ma lampang z axis in ti hian hei ka varot ta ne ti hian x le y direction in tin ka tik ka rot kwal ta khami. The turning effect of force about the axis of rotation x le y direction kami kavanem kwal mo kavanor kavarot dip ani so kavarot vak na x rotation ha. The turning effect of force about the axis of rotation, that you are taking two axes in this case, right? So the turning effect het ten chung le noi jong tin kavarot ta vak ta khateng ha the cover force pe ka kha. The turning effect of force about the axis of rotation is simply called moment of force. Okay, and it can be measured, so it is also called torque, and torque is measured as the product of force. Okay, it is measured as the product of force and the perpendicular distance from the axis of rotation. Okay, force into distance or displacement. So what will be the perpendicular distance? It is, so consider a particle in an xy plane. Okay, consider a particle in an xy plane, and at the point P. Okay, and whose position vector is the position vector of the particle at point P. Let it be r vector. Okay, the position vector is r vector, and the position makes an angle. The position vector makes an angle theta with the x plane. Okay, with the x plane, and what will be the perpendicular distance? The perpendicular distance will actually be, this is not perpendicular yet, right? So this is the axis of rotation. Okay, this is the point of rotation. So the perpendicular distance will be up to here. So here it is 90 degree, right? So this distance d is the perpendicular distance from the axis of rotation. This cannot be the distance, okay, since it is not perpendicular. Okay, this is the perpendicular one, and let the angle over here, let it be phi. Okay, phi. Now so what is from the definition of force? Torque is measured as the product of the force and the distance of rotation, right? And so what is torque? Torque is represented by a Greek letter tau. Okay, this is called tau, but we can also pronounce it as torque. Okay, this is the symbol for torque. And what is force? Force can be simply F, right? And for distance, the distance of the point P from the axis of rotation is from the point of rotation, the distance of the particle is r, right? So F cross r. This is the easy derived way to solve the value of torque. Now if the torque is, if we remove the vector, okay, if you're going to write it in terms of magnitude, okay, so if you're going to write it in terms of this is in vector form, right? So in terms of magnitude, so we can write it like, let me write r first. Okay, rf. If I'm going to remove the vector sign, then I have to take rf sine phi. Okay, so why sine? Why not cos? Okay, sine. If you look at this right triangle, if we take this angle phi, okay, this one is the perpendicular, right? And this is the hypotenuse, right? So some people have, okay, so that is why we are taking sine. Okay, if it is cos, then it will be curly brown hair, right? This will be the base. So this is not needed. What we need is the perpendicular distance from the axis of rotation, from the point of rotation, and the distance of the particle, right? So we need perpendicular and hypotenuse, so we are taking sine. Now again, what is r sine phi? Okay, let me put f in the beginning. R sine phi, let me take it over here. So what is r sine phi actually? R into sine phi means r into, what is sine phi again? Some people have, right, perpendicular by hypotenuse, right? So d by r. I remove the vector. Okay, we are solving in terms of magnitude, so here r and r will cancel. So actually r sine phi means d, right, this distance. So we can, instead of r sine phi, we can simply put fd, right? So torque is equal to force into, this is called, this distance, the perpendicular distance about the, from the point of rotation, this distance is called moment arm. Okay, this is called moment arm. So actually, what is, from inwards, we can write that torque is also equal to the force into moment arm. Okay, moment arm. Okay, now if we solve it into two components, okay, if we resolve this r vector into two components, if it goes straight like this, right, then, or if it goes in the direction of theta, okay, if it goes in the direction of theta, then it will be, this one will be, let it be fr, okay, this direction, this force, and here let it be f theta, right? So here theta, fr and f theta, fr is called the radial component, okay, of force, and f theta is called the transverse component of force. Okay, so if we resolve this force into two rectangular components, okay, so fr and f theta, then fr will be equal to f cos phi. Okay, so this will still be cos, okay, so sorry, this will still be phi because it is vertically opposite angle. Okay, so and f theta will be equal to f sine phi. Okay, now from this equation, okay, from this equation, what do we have for f theta? What do we have for torque? Torque is equal to r f sine phi, right? So from this equation, we have torque is equal to, let me put f sine phi together in this case. Okay, f sine phi, let me put it together, and r, let me put it separately. So what is f sine phi? F sine phi is f theta, right? So it will be f theta r. Okay, so this is just what to say, additional steps. Okay, these are not very, you know, important or necessary steps for this particular topic. These are just like additional notes. Okay, these are just like additional steps to make it more detailed. Okay, so what is important here is torque is the product of force into distance. Okay, the turning effect of force about the axis of rotation. Now in the next topic, we have angular momentum. Okay, so I have just finished explaining about moment of force, torque, which symbol is this. Okay, and before I go into the next topic, the SI unit of torque is Newton meter. Okay, the SI unit of torque is Newton meter, and the dimensional formula is ml square t minus 2. Okay, I will not explain how we get this since we have talked about it in many times. Okay, so the SI unit is Newton meter and the dimensional formula is ml square t minus 2. Now our next topic is angular momentum, and it is somewhat exactly the same with this moment of force. Okay, if you are familiar with the moment of force, then it means that you are familiar with angular momentum. So we will be talking about angular momentum. It is somewhat the same as the previous topic. Okay, so the turning movement of a particle about the axis of rotation. Okay, torque kanti kasuna force lampang khani ta tro hemi kil khata about the axis of rotation. The force can apply na a force za ta khani ta ni torque kan ti kha chuan angular momentum ani hi chuan a movement ta khani thungang the turning movement of particle about the axis of rotation khami a particle a che dan motion a kha khalai kha angular momentum chuni thung ta ni the turning movement of a particle about the axis of rotation. So we will take again two dimensional axis x and y, and this angular momentum we just simply represent it by L. Okay, and so from the definition it is noted by L, and angular momentum is can be measured as the product of linear momentum. Angular momentum can be measured as the product of linear momentum and perpendicular distance. Okay, perpendicular distance about the axis of rotation. Okay, perpendicular distance or perpendicular displacement from the axis of rotation. So before I go into detail, the SI unit of angular momentum is kg meter square per second. Okay, kg meter square per second, and the dimensional formula is ml square t minus 1. Okay, this is the dimensional ml square t minus 1. Now it is a vector quantity, and now consider a particle in an xy plane, a particle at the point P again. So let the position vector from the origin, let it be r again. Like I said, it's somewhat exactly the same with the previous one. Okay, and let the position vector make an angle theta with the x-axis, and let the linear momentum of the particle be p. Okay, let the linear momentum of the particle be p. So what will be the perpendicular distance from the axis of rotation? Again, we'll go perpendicularly, right? Perpendicular distance here will be d, right? So from the definition of angular momentum can be, like I said, the symbol is L, right? So angular momentum is the product of linear momentum and perpendicular distance, right? In this case, let us take this r, okay, the distance. So r, p cross r, okay, the product. Now again, if you're going to write it in terms of magnitude, it means that if you're going to remove the vector sign, we will take, let me write r first, okay, rp, p sine phi. Okay, let's give this equation 1, and let's give this equation 2. This is in terms of magnitude. I will not explain how we get sine again. Okay, it is exactly the same with the previous topic. Now again, r sine phi, r sine phi will be again equal to, what is sine? Some people have, right, d by r. So r sine phi will be equal to d. Okay, so we can write L equals to, since r sine phi is d, we can write bd, right? So from here we can write in words again, angular momentum is equal to linear momentum into, what is the perpendicular distance, right? Perpendicular distance from the axis of rotation. So we are proving this definition. Okay, now if the momentum, okay, if the momentum at this point P, if the linear momentum has been resolved again into two components, okay, so if it is resolved into two components, PR and P theta, okay, if it is resolved into two components, PR and P theta, in the direction of the increase of R, okay, R here, this is R, right? So it is increasing in this direction, so it is PR, and in the direction of theta, okay, increase in theta, theta is this direction, right? So P theta is this one. So if I draw straight again like this, right, this will still be phi. So they are vertically opposite angles. So let this be P, they are vertically opposite angle, so it will still be phi. So this is exactly the same. The figure is also heta ka draw kha ay boy chuar de ule ka mohar me the textbook ne lo tang kop ve ula heta kan draw dan hoi ang che tho ni eng ma dang lam na om lo. Then PR is called again radial radial component of linear momentum, okay, and p theta is called transverse component of linear momentum. And we can prove that PR is equal to P cos phi and P theta is equal to P sin phi, right? Now from equation 2, we have L equal to RP sin phi. So P sin phi, right? So from this equation 2, what will L equals to, since P sin phi is equal to P theta, so we can write P theta R, right? So again, from here, what can we write? We can write that angular momentum, okay, angular momentum is L, right? Angular momentum is equal to the product of what is R? R is the distance of this, R is the distance from the axis of rotation, right? R is the distance from axis of rotation. And what is P theta? P theta is, PR is radial component of linear momentum, and P theta is, again, like I said, transverse component, right? So in words, we can say that P theta is transverse component of linear momentum, transverse component of linear momentum, okay? So we can write angular momentum is equal to transverse component of linear momentum into distance from axis of rotation. So just like that also we can define this one, okay? Torque, okay, that moment of force or torque is equal to transverse component of force and distance of particle from the axis of rotation, okay? So theta is transverse, okay? So these are just simple definitions and simple derivations, okay? Now let's go to our next topic. This may be important for around 2 or 3 marks, okay? Relation between torque and angular momentum. Now we will derive the relation between torque and angular momentum. What is the angular momentum? The angular momentum is here. Angular momentum is R cross P, right? So we have the definition of angular momentum. We have angular momentum is equal to R cross P, okay? Now we will differentiate both sides. The next step is differentiation, okay? Just remember the steps. It's very simple. The next step is differentiating both sides with respect to t. So it will be d by dt of L, right? D by dt of L. Atho hi kaziak vak lawan ma se exam na chon ti han ti ka tiang pok hi chon ron ti lo la makin ma chengo tang he te ka tianga kaziang che chen ron zia ve rengo chon athu ka ra ka soi ho le a step kal phung kha chu nang manin in onward top ve me nga construct chop ve me nga consider a body ti ang chi te khateng chi neu kha chu textbook ang che ron zia chua kher tum po kha ngai lawa a derivation lai hi poimo awang khane ka explain chip che ra ni me thu jong kha chu ka ziak seng bik lawa chuma chon exam na po chan dan khain lo thiam don ne. Now we will differentiate both sides with respect to t. So the dl by dt, right? So is equal to d by dt of r cross p, okay? Now how will we differentiate cross product? So the next step will be dl by dt is equal to differentiation of first, okay? First we will differentiate the first one, dr by dt into second. The second is all differentiate ve nga lo tur a formula ve top first into second plus second into first, okay? Differentiation of first term into second plus differentiation of second term, okay, dp by dt into first term, okay? That is just the simple formula of differentiation of two variables, two products. Now what is dr by dt? Dr by dt, r is distance, right? R represents the distance or the displacement. So dr by dt is displacement by time, right? So what is displacement by time is velocity, okay? That is the definition of velocity. And dp by dt, this is Newton's second law of motion, right? Rate of change of momentum with respect to time. That is that is force, right? This is Newton's second law of motion. So we will substitute, in case of dr by dt, we will substitute v, and for dp by dt, we will substitute f, okay, force. So what will we have? If we substitute these two values, then in this line, we will have dl by dt is equal to v cross p, right, plus this is force, right, f cross r. Now v and p, velocity and momentum, okay, velocity and momentum, they never touch each other, okay, they are parallel vectors, okay. So what happens for the case of two parallel vectors, parallel vector at one, for the case of two parallel vectors, the cross product is 0 ni, oh, parallel rang one, their cross product is 0, okay. So since v and p are parallel to each other, then this value will be 0, okay. So what will we have? dl by dt will be equal to f cross r, right? Now what is f cross r or r cross f? If we look back at our previous explanation here, f cross r or r cross f is torque, right? Torque also we can put vector sign, okay. So this is the moment of force. So instead of this again, I can write torque. dl by dt is equal to torque, okay. So this is the relation between angular momentum is L, and this is the torque, okay. So our topic is relation between torque and angular momentum. So how can we write the relation? The angular momentum, the time rate of change of angular momentum, L ringot ko angular momentum niya, mas can differentiate big tahe to time in so on. The time rate of change of angular momentum is equal to the torque, okay. So that is the relation. Torque on a particle is equal to the time rate of change of angular momentum, okay. So that is the relation between torque and angular. If we differentiate angular momentum with respect to time, then it will be equal to torque, okay. So that is the simple relation between torque and angular momentum. We are almost finished, okay. Now let's talk about the law of conservation of angular momentum. Law of conservation of momentum. Firstly, I will say the statement, okay. Law of conservation of angular momentum states that if no external torque acts on the system, okay, it means that if torque is 0, okay, if no external torque or moment of force acts on the system, then the angular momentum of the system, okay, the total angular momentum of the system will be 0, okay, or will be conserved, okay, that is, or will remain conserved. That is the law of conservation of angular momentum. So now consider a system of n particles. Again, consider a number of particles up to n, right? Now if no n under the action of torque, okay, under the action of torque due to external, and suppose that the particles of a system, and this number of particles, suppose that these particles of the system are under the action of torque, okay. This number of particles of a system are under the action of an external force acting on it, right? So if dl by dt is the rate of change of angular momentum, okay. So if dl by dt is the rate of change of angular momentum with respect to time, then what do we have from their relation? From our just previous topic, the relation is torque is equal to dl by dt, right? So external torque is equal to dl by dt. This is the relation, right? But if in case the external torque is of the system is 0. Okay, so in case if this external torque is 0, then what does that mean? It means that dl by dt will be 0, right? In case if the external torque is 0, it means that dl by dt will also be 0. Okay, now if L1, L2, L3 up to Ln, okay, if they are the angular momentums of different particles, okay, like I said, there are n number of particles, right? So if L1, L2, and L3, Ln are the angular momentums of the different particles, then in that case, L1, the sum of the angular momentum, up to Ln, right, it will be constant. So this is just a simple mathematical representation for the law of conservation of angular momentum. Okay. In fact, yam long me thema se a whole to go hitu. That's what pon mark ni vel back base omlowa put mo. A statement in us so a law of conservation of angular momentum in us so ber to torque, external torque force ti khathawani ko torque omlo chuan angular momentum hi 0 ni atia. Chuan unrelation a khan torque hi rate of change of angular momentum matni ta ni. Chuan torque hi 0 ni miau chuan chu statement a if no external force x, if no external torque x on the system ati torque miau lo chuan hi chu 0 ni ani don ti na ne. Chuan enganga tam n particles po linear momentum so kha ln thleng po ni se belvek pon torque ber 0 ni chuan 0 chhuak don chuan constant value mo chuan kha statement on the law of conservation of linear angular momentum states that if no external torque x on the system, then the total angular momentum of the system will remain conserved or will be constant. Okay, so that is the statement. Now for our final topic, let's talk about moment of inertia. Moment of inertia of a rigid body. Okay, so what is the definition of moment of inertia? Moment of inertia, before I explain the definition, let us consider a rigid body. Okay, let us consider a rigid body and in the OZ plane. Okay, it is in 3 dimension and it is along the OZ plane, z-axis, and let the number of particles be up to n. Okay, and let the mass of the particles be m1, m2, m3 up to mn. Okay, let the number of particles be up to n and let their masses be m1, m2, m3 mn, and let their distance from the z-axis, let the distance of these particles be r1, r2, r3 up to rn, right, respectively. So the moment of inertia how will we define moment of inertia? The moment of inertia of a rigid body is the sum of the product of the masses. Okay, it is the sum. Okay, sum means plus. It is the sum of the product of the masses, each of the masses, and the squares of the distance. Okay, and the squares of the distance. Mass 1 is, the distance is r1, right? So it will be r1 square, right? Square of the distance. So mass 2 is r2 square. Mass 3 will be r3 square, like that, up to mn rn square, right? So the moment of inertia we just represented by I. Okay, capital letter I. So the moment of inertia of a rigid body is the sum of the product. Okay, in multiplies here, the mr ka. It is the sum of the product of the masses of the various particles. Okay, the particle is having the object is having many particles, right? In the body there are many particles, n number of particles in one body. So the moment of inertia is defined as the sum of the product of the masses of the particles and the squares of the distances of not just any distance, of the perpendicular distance, right? Straight distance of the perpendicular distances from the axis of rotation. Okay, and rotate na a chet na axis point atanga te a perpendicular he atanga heti han te chho ni loin perpendicular anga ya wangi tin ngilin mo. So that is, if you know how to say this in words, that will give the definition of moment of inertia. Okay, it is the sum of the product of the masses of the various particles and the squares of the perpendicular distance from the axis of rotation. Okay, perpendicular distance. It is the definition of moment of inertia. And in other words, it is put low here, we can also represent it by summation I going from 1 to n. Okay, I going from I equal to 1 heta chunga n kan zil na soidan taka chuan I going from 1 to n, no 1 atanga n thlengin tina a summation mo bel vector tong kam het yang symbol henaron wholesale ani chu haron lakim vek. So we can rewrite it like mi ri square, right? Since it is in this form, right? So summation I going from 1 to n mi ri square. So we can also represent moment of inertia of a rigid body in this way. And the moment of inertia of is in CGS system is gram centimeter square. Okay, and in standard system it is kg meter square, and the dimensional formula is ml square. Okay, there is no time. Okay, there is no time. Okay, so we can or we can, if you want to add time, then it will be t0. Okay, so this is the dimensional formula. We will not be studying a very long topics or very long derivations. So this, I feel this will be enough from this unit.